What if I told you that right now, at this very moment, there's a massive thermonuclear explosion happening just 93 million miles away from you? An explosion so powerful that it's been continuously burning for 4.5 billion years, releasing more energy every single second than humanity has used in our entire existence. And this explosion is so bright that even though it's nearly 100 million miles away, you can't look directly at it without damaging your eyes permanently within seconds. This explosion has the power to destroy all life on Earth in an instant if it wanted to. And yet, it's also the reason why life exists on Earth at all. Every breath you take, every plant you see, every bit of food you eat, every drop of gasoline in your car, all of it is powered by this explosion. And here's the crazy part. Most people go their entire lives never really seeing what this explosion actually looks like up close. They see a bright yellow circle in the sky, and that's it. But today, I'm going to show you what I saw when I pointed my camera directly at this explosion. And what I captured will absolutely blow your mind. I'm talking about massive dark spots on the surface that are each larger than planet Earth. I'm talking about towers of superheated plasma that rise hundreds of thousands of miles above the surface, held in place by magnetic fields so powerful they would rip the iron from your blood if you got too close. I'm talking about explosions on the surface that release more energy than 1 billion nuclear bombs going off simultaneously. And the most incredible part, I captured all of this from my backyard, using equipment that anyone can access. And by the end of this video, you'll know exactly how I did it and how you can do it too. The sun, our star, the center of our solar system, the source of all energy and life on Earth. We see it every single day, rising in the east, crossing the sky, setting in the west, and yet most of us have never truly seen it. We've never seen the boiling, churning surface where plasma rises and falls in massive convection cells. We've never seen the dark, cooler regions where intense magnetic fields suppress the flow of heat. We've never seen the spectacular eruptions and prominences that arch hundreds of thousands of miles into space. We take the sun for granted because it's always there, reliable, predictable, unchanging, or so we think. But the truth is, the sun is one of the most dynamic, violent, and fascinating objects you can observe. And when you point a camera at it with the right equipment and techniques, you discover a whole new world. A world of incredible beauty, terrifying power, and endless fascination. This is the story of how I captured that world, how I took this video of the sun, and everything I learned along the way about our nearest star and the incredible challenge of photographing it. Before we dive into the technical details of how I captured these images, I want you to understand why the sun is so absolutely extraordinary and why it's worth the effort to photograph it properly. The sun is not just a ball of fire in the sky. It's not burning like a campfire or a candle. What's happening inside the sun is far more powerful and far more incredible than simple combustion. The sun is a massive nuclear fusion reactor where hydrogen atoms are being crushed together under such extreme pressure and temperature that they fuse into helium atoms. And in that process, they release energy according to Einstein's famous equation. Energy equals mass times the speed of light squared. That equation tells us that even a tiny amount of mass can be converted into an enormous amount of energy. And the sun is converting about 4 million tons of matter into pure energy every single second. Think about that for a moment. 4 million tons of matter simply ceasing to exist and transforming into light and heat every second. That's like 65 billion kilograms per minute being converted to energy. More mass than all the buildings in a major city, just vanishing and becoming light. And this process has been going on continuously for 4.5 billion years. And it will continue for another 5 billion years before the sun runs out of hydrogen fuel, the energy produced in the sun's core, where temperatures reach 50 million degrees Celsius, doesn't immediately reach us here on Earth. That energy takes a journey that lasts hundreds of thousands of years as it slowly works its way from the core through the sun's interior, bouncing around in a process called radiative transfer, where photons are absorbed and re-emitted countless times by the dense plasma. Eventually, the energy reaches the outer layers of the sun where convection takes over. Hot plasma rises to the surface, cools slightly, and then sinks back down, creating the granulation pattern that we can see when we image the sun at high resolution. These granules are enormous, each one typically about 1,000 kilometers across, which means they're roughly the size of Texas or France, and they're all moving, rising and falling, constantly changing, creating a boiling, dynamic surface that's never the same from one moment to the next. When that energy finally reaches the sun's visible surface, called the photosphere, it's in the form of light and heat that then travels through space for 8 minutes and 19 seconds before reaching Earth. Which means that when you look at the sun, you're not seeing it as it is right now. You're seeing it as it was about 8.5 minutes ago, but the sun's influence extends far beyond just providing light and heat. The sun generates a powerful magnetic field, and this field becomes twisted and tangled by the differential rotation of the sun's surface. The equator rotates faster than the poles, which creates complex magnetic structures that burst through the surface and create what we see as sunspots, prominences, and solar flares. These magnetic phenomena are not just pretty to look at, they have real consequences for us here on Earth. When the sun produces a powerful solar flare or ejects a massive cloud of plasma in what's called a coronal mass ejection, that material and radiation can travel through space and interact with Earth's magnetic field, creating beautiful auroras near the poles but also potentially disrupting satellites, interfering with radio communications, and in extreme cases, even damaging power grids and causing widespread blackouts. This is why solar observation and monitoring is not just a hobby for amateur astronomers. It's an important scientific endeavor that helps us understand and predict space weather that can affect our technology-dependent civilization. The sun, also, goes through cycles of activity that have fascinated humans for centuries. The sunspot cycle, also called the solar cycle, is an approximately 11-year cycle during which the sun alternates between periods of high activity and low activity. During solar maximum, the sun's surface is often covered with numerous sunspots. Active regions produce frequent solar flares, and spectacular prominences are common. During solar minimum, the sun can go days or even weeks without a single visible sunspot, and the surface appears relatively calm and quiet. These cycles have been observed and recorded since Galileo first pointed a telescope at the sun in the early 1600s and discovered sunspots, proving that the sun was not a perfect, unchanging sphere as ancient philosophy had claimed, but rather a dynamic object subject to change and evolution. We're currently in solar cycle 25, and we're approaching solar maximum, which is scheduled to occur sometime around 2025, which means that right now is actually an excellent time to be observing and photographing the sun, because there's so much interesting activity to see and capture. Understanding all of this context makes solar photography so much more meaningful. You're not just taking pretty pictures, you're documenting the behavior of a massive nuclear furnace that determines whether life on Earth can exist. You're capturing magnetic phenomena that can affect technology across our entire planet. You're recording data that contributes to our understanding of stellar physics and helps us predict space weather, and you're connecting with a tradition of solar observation that goes back centuries, following in the footsteps of astronomers like Galileo, who risked his eyesight to study the sun, and modern solar physicists who use sophisticated instruments to monitor our star continuously. Every image you capture is a snapshot of a moment in the life of a star that has existed for billions of years and will continue to exist for billions more, but which is constantly changing on time from seconds to decades to eons. Now that you understand why the sun is worth photographing, let's talk about why photographing the sun is so incredibly challenging, and why it requires completely different techniques than almost any other type of photography. The first and most obvious challenge is the intensity of sunlight. The sun is extraordinarily bright, about 400,000 times brighter than the full moon, and all of that light is concentrated into a relatively small area of the sky, only about half a degree in angular diameter. When you point a camera or telescope at the sun without proper protection, all of that light and heat gets focused down onto your camera's sensor, or if you use an optical viewfinder, onto your retina. The camera sensor can be damaged instantly. Pixels can burn out, coatings can melt, and internal components can overheat. If you're looking through an optical viewfinder, the consequences are even more serious. The concentrated sunlight can cause permanent retinal damage in less than a second, leading to blind spots, vision loss, or complete blindness. This is not an exaggeration or something to take lightly. The sun is dangerous, and you must treat it with respect. The solution to the intensity problem is specialized solar filtration, but this introduces its own set of challenges. Solar filters must block out more than 99.9% of the sun's light, while still allowing through enough light to form an image. These filters are typically made from either specialized glass with metallic coatings or from polymer film with precisely controlled optical properties. The filters must be absolutely free from any defects, pinholes, scratches, or damage, because even a tiny flaw can allow through enough concentrated sunlight to cause damage. Before every single imaging session, you must carefully inspect your solar filter to ensure it's in perfect condition, and you must make absolutely certain that the filter is securely attached to your telescope or camera lens before ever pointing it toward the sun. There are no second chances with solar safety, and no image is worth risking your eyesight or damaging your equipment. Beyond the safety challenges, there are significant technical challenges that make solar imaging one of the most demanding forms of astrophotography. The first major challenge is atmospheric turbulence, often referred to by astronomers as seeing conditions. The Earth's atmosphere is constantly in motion, with layers of air at different temperatures moving past each other, creating turbulence that distorts light as it passes through. This is the same phenomenon that causes stars to twinkle at night, but during the day, when the sun has heated the ground and created strong thermal convection, the atmospheric turbulence is typically much worse. When you look at the sun through a telescope at high magnification, you can literally see the image boiling and distorting in real time, as turbulent air masses move across your line of sight. One moment, the image might snap into perfect sharpness, revealing incredible detail, and the next moment, it's a blurry, distorted mess as a wave of turbulent air passes by. This atmospheric interference means that capturing sharp, detailed solar images requires not just good equipment, but also good timing, patience, and sophisticated image processing techniques that I'll explain in detail later. Another challenge, unique to solar imaging, is the sun's brightness uniformity, or rather, the lack of it. The sun's surface has an enormous range of brightness levels, from the extremely bright photosphere to the much darker cores of sunspots, which can be 100 times dimmer than the surrounding surface, to the even darker umbra in the centers of large sunspots. Capturing detail across this entire brightness range in a single image is extremely difficult. If you expose your camera to properly capture the bright photosphere, the sunspots become pitch black with no visible detail. If you expose to bring out detail in the sunspots, the photosphere becomes completely overexposed, blown out, with no texture or detail visible. Professional solar observatories deal with this by using specialized instruments that can adjust exposure across different parts of the image, but for amateur solar photographers, we have to use careful exposure, control, and sometimes combine multiple exposures with different settings to capture the full range of detail. The sun is also constantly moving across the sky due to Earth's rotation, and when you're viewing it at high magnification through a telescope, this apparent motion is surprisingly fast. Without a tracking mount, the sun will drift completely out of your field of view in just a few minutes, forcing you to constantly manually adjust your telescope's position. This makes capturing stable, steady footage nearly impossible and introduces vibration and shake every time you touch the telescope to recenter the sun. Professional equatorial mounts solve this problem by automatically tracking the sun's motion across the sky. But these mounts are expensive, require careful alignment, and add complexity to your setup. For beginners working with simpler equipment, dealing with the sun's motion across the field of view is one of the most frustrating aspects of solar imaging. There's also the challenge of focus, which becomes exponentially more difficult at the high magnifications needed for detailed solar imaging. When you're magnifying the sun enough to see individual sunspots in granulation, your depth of focus becomes razor thin. Sometimes just a few millimeters of movement in your focuser can take you from perfect focus to completely blurry. Achieving and maintaining perfect focus requires a steady hand, good focusing aids, and constant attention, because even small temperature changes can cause your telescope's focus to drift as materials expand or contract. Many solar imagers spend more time focusing than actually recording images, carefully tweaking their focuser position, waiting for moments of good seeing when the atmosphere stabilizes enough to judge focus accurately, and making tiny adjustments to squeeze out that last bit of sharpness. My journey into solar imaging began about 5 years ago, though my interest in astronomy goes back much further than that. I have been doing nighttime astrophotography for several years, capturing deep sky objects like nebulae and galaxies, imaging the moon in high resolution, and photographing planets when they were well positioned. I loved the challenge and the results, but I was frustrated by the limitations. Nighttime astrophotography requires clear, dark skies, which in many locations are only available on a fraction of nights throughout the year. Between weather, moon, phases, and light pollution, I found that I could only get out an image maybe once or twice a month, on average. I was hungry for more opportunities to practice and improve my skills, and I started researching solar imaging as a way to do astronomy during the daytime, taking advantage of clear days that would otherwise be wasted from an astrophotography perspective. The more I learned about solar imaging, the more fascinated I became. I discovered that the sun is not a static object but an incredibly dynamic one, with new features appearing and evolving every single day. I learned about the solar cycle and realized that we were approaching a period of increased solar activity, which meant there would be plenty of interesting features to observe and photograph. I saw images from experienced solar imagers that revealed details I had never imagined were visible from Earth. Granulation covering the entire solar surface, intricate structure within sunspots, spectacular prominences reaching hundreds of thousands of miles into space, and I knew I had to learn how to capture these phenomena myself. The technical challenge was also appealing. Solar imaging required different equipment, different techniques, and different processing approaches than nighttime astrophotography, which meant there was a whole new skill set to master. I started with modest equipment, just a simple white light solar filter that attached to my existing telescope and a DSLR camera. My first attempts were honestly pretty disappointing. The images were soft, lacking the sharp detail I had seen in examples from experienced imagers. The colors looked wrong. The sunspots were either too dark with no detail or washed out and barely visible. I struggled with focus, with atmospheric turbulence, with tracking the sun across the field of view. But I persisted, spending hour after hour reading tutorials, watching videos, asking questions in online astronomy forums, and practicing whenever the weather cooperated. Slowly but surely, my results improved. I learned about atmospheric seeing and how to identify the best imaging conditions. I learned about the importance of high-speed video imaging and frame stacking. I invested in better equipment, upgrading from my DSLR to a dedicated planetary camera, adding a motorized equatorial mount for precise tracking, eventually upgrading to a specialized solar telescope with HL5 filters that could reveal prominence, detail invisible to standard white light imaging. Each improvement in my equipment and technique opened up new details that I hadn't been able to capture before. When I first captured clear granulation across the solar surface, seeing those convection cells in detail for the first time, I was absolutely thrilled. When I captured my first prominence, seeing that arch of plasma suspended above the solar limb, held aloft by invisible magnetic fields, I was hooked forever. And when I captured a solar flare in progress, seeing that sudden brightening in an active region that lasted only minutes before fading away, I realized that I wasn't just taking pictures. I was witnessing and documenting real, significant solar events as they happened. The more I learned and the better my images became, the more I wanted to share this knowledge with others. To help people understand that the sun is not just a boring yellow circle in the sky, but an incredibly complex, beautiful, and fascinating object that anyone can observe and photograph if they're willing to invest the time to learn the proper techniques. Let's start with the most critical piece of equipment for any solar imaging setup, the solar filter. I cannot emphasize enough how important this is. The solar filter is not optional. It's not something you can skip or compromise on. It's the single most essential piece of safety equipment that protects both your eyes and your camera from the sun's intense radiation. There are several types of solar filters available, each with their own characteristics, advantages, and price points. So let me break down the options and explain what I use and why. The most common and affordable option for beginners is a white light solar filter made from Boucher solar film or similar polymer material. This specialized film is coated with a metallic layer that reflects away most of the sun's light while allowing through a safe amount for imaging. The film comes in two varieties, visual density and photographic density. Visual density filters are designed for safe visual observation and block out about 99.999% of the sun's light, creating a neutral white or slightly blue appearance of the sun. Photographic density filters block slightly less light, around 99.996%, which allows for shorter exposure times when imaging, though both types are perfectly safe for both visual use and photography. The beauty of solar film is that it's relatively inexpensive. You can purchase sheets of it and create your own filter cell to fit your specific telescope or camera lens. And the optical quality is excellent when handled properly. When I first started solar imaging, I made my own filter using Boucher Astro Solar Safety Film. I purchased a sheet of the material, which came with detailed instructions for construction. And I built a simple filter cell using cardboard, foam board, and tape. The key is creating a rigid frame that holds the film perfectly flat without any wrinkles or stress, and ensuring that the filter cell fits securely over your telescope aperture with no possibility of it falling off or being blown off by wind. Some people use PVC pipe, others use foam core board, and some just purchase pre-made cells where you can insert the film. Whatever method you choose, the critical factors are that the film must be completely defect-free. You need to inspect it carefully against a bright light, looking for any pinholes or scratches. The film must be mounted flat without wrinkles, but would distort the image? And the cell must attach securely to your telescope with no way for unfiltered sunlight to enter the optical system. I also recommend creating a backup filter as a spare, because if your primary filter gets damaged during an imaging session, you want to be able to continue observing rather than having to pack everything up. Another popular option for white light solar imaging is glass solar filters. typically made from specialized glass with metallic coatings, such as those using Thousand Oaks opticals, solar light film, or Boucher planetariums. ASTF series glass filters. Glass filters are more expensive than film filters, but they offer some advantages, including more robust construction that's less susceptible to damage, better optical flatness, which can improve image quality, and a variety of transmission characteristics that produce different color renditions of the sun. Some glass filters produce a neutral white image, others create an orange sun, and some specialized filters can enhance certain solar features. The downside of glass filters is the cost. They're significantly more expensive than film filters, especially for larger apertures. And they're heavier, which can create balance issues on some telescope mounts. For most beginners, I recommend starting with film filters to keep costs down, and then potentially upgrading to glass filters later. If you find you're serious about solar imaging and want the convenience and durability of glass beyond standard white light filters, there's an entirely different category of solar filters called narrowband or hydrogen alpha filters. And these open up a completely different view of the sun. Hydrogen alpha filters are specialized interference filters that only allow through an extremely narrow wavelength range centered on the hydrogen alpha emission line at 656.3 nanometers. At this wavelength, you can see features that are completely invisible to white light imaging, including prominences extending above the solar limb, filaments crossing the solar disk, plages surrounding active regions, and active region structures that appear much more dramatic in H-alpha than in white light. The view through an H-alpha telescope is absolutely stunning. The sun appears bright, red-orange, and prominences that are invisible in white light suddenly appear as dramatic arches and loops, extending hundreds of thousands of miles above the solar surface. However, H-alpha imaging equipment is substantially more expensive than white light equipment. Dedicated H-alpha telescopes typically start around $1,000 for small aperture systems and can cost $5,000 to $10,000 or more for larger high-quality systems. The filters themselves are complex and expensive to manufacture because they must block all wavelengths, except for that tiny slice around H-alpha, and the blocking must be extremely effective or else the bright, white light photosphere will overwhelm the fainter H-alpha features. I eventually invested in a dedicated H-alpha telescope after a year of white light imaging, and it completely transformed my solar observing experience. Being able to see prominences in real time, watching them change and evolve over the course of an imaging session, capturing the delicate structure of filaments snaking across the solar disk, it justified every penny of the investment. But I always recommend that beginners start with white light imaging first. Learn the basics of solar observation, focusing, atmospheric seeing, and image processing before investing in more expensive H-alpha equipment. The skills you develop with white light imaging translate directly to H-alpha work, and you'll have a much better understanding of what features you're looking at and how to capture them effectively. Once you have a proper solar filter sorted out, the next critical component is your telescope or lens system. The good news is that unlike many forms of astrophotography where you need large apertures to gather enough light from faint deep-sky objects, solar imaging actually works quite well with modest aperture telescopes. The sun is extraordinarily bright even through a solar filter, so light-gathering power is not your limitation. Instead, your primary concerns are optical quality, focal length, and aperture for resolving fine details. Let me break down the different types of optical systems that work well for solar imaging and explain the trade-offs involved in each approach. For photographers who already own telephoto lenses, the simplest entry point to solar imaging is to attach a proper solar filter to your existing camera lens and use that for full-disk solar imaging. A focal length of 400 to 600 millimeters is ideal for capturing the entire solar disk with some space around the edges to frame the image nicely. You'll need either a commercially available solar filter that fits your lens diameter, or you can create your own filter cell to attach to your lens. The advantages of this approach are simplicity and low cost. If you already own suitable lenses, and the ability to capture full-disk images that show the overall structure and distribution of solar features. The disadvantages are limited magnification. You won't be able to see fine details like granulation or subtle sunspot structure. And most camera lenses are not designed for the highest possible optical quality, so you may see some chromatic aberration, particularly near the edges of the solar disk, and other optical artifacts that degrade fine detail. For more serious solar imaging, dedicated telescopes offer significant advantages. Refractor telescopes, which use lenses rather than mirrors, are particularly popular for solar work because they produce images with excellent contrast and don't have the central obstruction that reflector telescopes have. A good quality with an aperture of 70 to 100 millimeters and a focal length of 500 to 1000 millimeters. provides an excellent balance for detailed solar imaging. The apochromatic refractors, or APO refractors, use specialized glass elements to minimize chromatic aberration and produce very sharp high-contrast images with minimal color fringing. These telescopes tend to be expensive, but they're the gold standard for planetary and solar imaging. My primary white light imaging setup uses a 90mm APO refractor with an 800mm focal length, which gives me enough magnification to see granulation clearly while still fitting the entire solar disk in my camera's field of view. For H-alpha imaging, you'll want a dedicated solar telescope with a built-in H-alpha filter system. These telescopes come as complete packages with a narrowband filter permanently integrated into the optical path, and they're specifically optimized for H-alpha wavelengths. The most popular manufacturers of H-alpha solar telescopes are Coronado, Lunt Solar Systems, and Daystar. These telescopes come in various apertures ranging from 40mm up to 150mm or more, with correspondingly different price points. The aperture determines not just magnification but also the brightness of the H-alpha image, which is important because H-alpha features are relatively faint compared to the bright white light photosphere. Larger aperture H-alpha telescopes can reveal more subtle details and prominences and surface features, but they cost substantially more than smaller systems. Most amateur solar imagers start with a 60 or 70mm H-alpha telescope, which provides excellent views of prominences and major surface features while remaining affordable. One important specification, to understand when choosing an H-alpha telescope is the bandwidth, measured in angstroms, which indicates how narrow the wavelength range is that the filter transmits. Narrower bandwidths reveal more solar detail, particularly surface features like filaments and plages. But they also result in dimmer images because less light is getting through the filter. H-alpha telescopes typically come with bandwidths ranging from 0.4 angstroms to 1.0 angstroms or wider. For visual observing, a bandwidth around 0.7 angstroms offers a good balance between detail and brightness. For imaging, many people prefer narrower bandwidths like 0.5 angstroms because the camera can handle the lower light levels with longer exposures, and the additional surface detail is worth the trade-off. Some advanced systems include tunable etalons that allow you to adjust the wavelength slightly, which lets you tune across the H-alpha line to emphasize different features or to optimize the image for seeing conditions. Another consideration when selecting your optical system is whether you want to image just the sun itself or whether you also want to use the same equipment for other types of astronomy. Dedicated solar telescopes are optimized specifically for solar work and typically aren't suitable for nighttime astronomy. Refractors with removable solar filters can be used for both solar imaging during the day and planetary or deep sky imaging at night, which makes them more versatile, though potentially not quite as optimized for any one purpose. When I was starting out, the versatility of a standard refractor appealed to me, and I'm glad I went that route because it gave me one excellent telescope that I could use for multiple types of imaging. Later, when I knew I was committed to solar imaging, I invested in a dedicated H-alpha telescope specifically for solar work while keeping my refractor available for nighttime. Projects. The camera you choose for solar imaging might be very different from what you'd use for other types of photography, and understanding why requires understanding the unique challenges of capturing solar detail. For general photography, we typically think about megapixels, dynamic range, low light performance, and color accuracy. For solar imaging, the priorities shift dramatically toward frame rate, sensor sensitivity, pixel size, and the ability to record high-speed video. Let me explain why these factors matter and what camera options are available. The fundamental technique used in modern solar imaging is called lucky imaging, and it's based on the reality that atmospheric turbulence is constantly distorting the image, but not uniformly. At any given moment, some parts of the image might be going through relatively calm air and appear sharp, while other parts are passing through turbulent air and appear blurry. If you record high-speed video, capturing hundreds or thousands of frames per second, you're essentially taking a massive number of snapshots of the sun, each one capturing a slightly different atmospheric condition. Later, during processing, you can analyze all these frames, identify the sharpest ones where the atmosphere happened to be calm, and combine only those best frames into a final image. This technique allows you to overcome atmospheric turbulence and produce images that are dramatically sharper than any single frame would be. To implement lucky imaging, you need a camera capable of recording high frame rate video. Standard DSLR cameras can work for solar imaging, and many beginners start with them because they already own one, but DSLRs have significant limitations. Most DSLRs are limited to 30 frames per second or less, and many can't record continuously for more than 10 or 15 minutes due to overheating or file size limitations. They also tend to have rolling shutter effects that can create distortions with fast-moving atmospheric turbulence, and their large photosites, while good for low-light performance, aren't ideal for resolving fine planetary and solar details. That said, if you're just starting out and want to see what the sun looks like through a filtered telescope, a DSLR is perfectly fine for initial experiments and learning the basics. For more serious solar imaging, dedicated astronomy cameras are a much better choice. These cameras use specialized CMOS sensors optimized for high-speed imaging. They can typically capture anywhere from 50 to over 200 frames per second, depending on resolution settings and sensor readout speeds. And they're designed to run continuously for extended periods without overheating. The most popular brands for planetary and solar imaging cameras are ZWO with their ASI camera line, the Imaging Source with their DMK and DFK cameras, and Player One Astronomy with their newer camera offerings. These cameras connect to your computer via USB. You control all the settings through dedicated imaging software, and they record video directly to your computer's hard drive, which means no file size limitations and no overheating issues. When selecting an astronomy camera for solar imaging, several specifications are important to consider.
First is the sensor size, which is typically smaller than the sensor in a DSLR or mirrorless camera. Common sizes are 1/3 inch, 1/2 inch, and 1 inch diagonal, with larger sensors providing a wider field of view but potentially lower frame rates. For full-disk solar imaging, a larger sensor is advantageous because it allows you to capture the entire sun at a comfortable magnification. For high-resolution imaging of solar details where you're zooming in on specific regions, a smaller sensor is fine and often preferable because it allows higher frame rates. Second is the pixel size, measured in microns. Smaller pixels can resolve finer details, but are less sensitive to light, while larger pixels are more sensitive but may not resolve details as finely. For solar imaging where light is abundant, smaller pixels around 2.9 to 4.6 microns are ideal for resolving granulation and fine sunspot details. Third is the bit depth and color capabilities. Many astronomy cameras offer both monochrome and color versions of the same sensor. Monochrome cameras are more sensitive because they don't have color filter arrays, and many advanced solar imagers prefer monochrome cameras combined with filter wheels for capturing separate red, green, and blue channels, or even narrowband H-alpha imaging. Color cameras are more convenient because they capture all color information in every frame, eliminating the need to use filters and recombine channels later, but they sacrifice some sensitivity and resolution. For beginners, I generally recommend color cameras for simplicity, and then potentially upgrading to monochrome with filters later if you want to pursue more advanced techniques. Fourth is the maximum frame rate and USB bandwidth. Higher frame rates mean you can capture more frames in less time, increasing your chances of recording moments of excellent seeing. But they also require more USB bandwidth and faster computer storage to handle the data. Most modern astronomy cameras use USB 3.0, which provides enough bandwidth for high frame rates with smaller sensor readouts. The camera currently used for white light solar imaging is a ZWO-ASI 178mm, which is a monochrome camera with a 1/3 inch sensor, 2.4 micron pixels, and capable of capturing up to 160 frames per second at full resolution. For H-alpha work, I use a ZWO-ASI 183mm with a 1-inch sensor, which gives me a larger field of view for capturing prominences. I also use various filters with my monochrome cameras, including an infrared pass filter that reduces atmospheric dispersion and improves sharpness by imaging in the infrared, where atmospheric turbulence has less effect, and of course RGB filters for capturing color images when I want them. This setup has served me extremely well, allowing me to capture the images you're seeing throughout this video. But I want to emphasize that you don't need the same equipment to get started. Many of the best solar images being produced by amateurs today are captured with much more modest gear. What matters most is understanding the techniques and being willing to practice and refine your approach before I even start setting up my equipment for a solar imaging session. There's a considerable amount of planning and preparation that goes into maximizing my chances of success. Unlike deep sky imaging, where you might plan weeks or months in advance around moon phases and weather forecasts, solar imaging planning is more dynamic and requires attention to several factors that can change day by day or even hour by hour. Understanding these factors and how to evaluate them will dramatically improve your success rate and the quality of your final images. The first factor to consider is atmospheric seeing conditions, which I mentioned earlier, but want to explore in much more detail because this is arguably the single most important factor determining whether you'll capture sharp, detailed images or soft, blurry ones. Atmospheric seeing refers to the optical stability of Earth's atmosphere, and is caused by turbulent air masses at different temperatures, mixing together along your line of sight to the sun. When cold and warm air masses collide and mix, they create regions of varying density, and thus varying refractive index, which bends light differently as it passes through. This causes the sun's image to shimmer, blur, and dance around in your telescope's field of view. On nights of poor seeing, stars twinkle violently and planets appear fuzzy and impossible to focus clearly. During the day, poor seeing manifests as the sun appearing to boil and shimmer, with details constantly dissolving and reforming as turbulent air masses move across your field of view. Several factors affect atmospheric seeing quality. Ground level heat is one of the biggest contributors to poor seeing during the day. After the sun has been up for several hours, it heats the ground, which creates rising columns of warm air and thermal turbulence. This is why the very best seeing conditions for solar imaging typically occur early in the morning, within the first hour or two after sunrise, before the ground has heated up significantly. During this early morning window, the atmosphere is often relatively calm and stable, giving you the best chance at capturing sharp images. As the day progresses and the ground heats up, seeing conditions generally deteriorate, though there can be brief periods of good seeing even in the afternoon if weather conditions are favorable. Late afternoon and evening, as the ground begins to cool, seeing conditions can sometimes improve again, though typically not to the same quality as early morning. High-altitude wind patterns also significantly affect seeing. The jet stream, which flows at altitudes of about 30,000 to 40,000 feet, can create turbulence that affects seeing even though it's far above us. Weather fronts moving through the area bring different air masses into contact and create turbulence. Even local geography matters. If you're imaging over a paved surface like a driveway or parking lot, the heat radiating from that dark surface will create terrible seeing right in your optical path. Imaging over grass or soil is better, and imaging near or over water, which doesn't heat up as quickly and creates more stable air, can provide excellent seeing conditions. Some dedicated solar imagers even set up near large bodies of water specifically to take advantage of the improved seeing. Fortunately, there are tools and resources available to help predict atmospheric seeing conditions. Before you commit time to setting up an imaging, several websites provide seeing forecasts based on atmospheric models, including Clear Dark Sky, which is popular among astrophotographers, and the NOAA's weather models, which predict atmospheric turbulence at various altitudes. These forecasts aren't perfect. Seeing conditions can be highly localized and can change quickly, but they give you a general idea of whether conditions are likely to be favorable or poor. I also pay attention to weather conditions like wind speed, temperature gradients, and recent precipitation. Days following rain systems often have excellent seeing as the atmosphere stabilizes, while hot, windy days typically have poor seeing. Over time, you'll develop an intuition for predicting seeing conditions based on local weather patterns and seasonal trends. The second major planning factor is solar activity itself. The sun is far from a static object. It's constantly changing, with new features appearing, evolving, and disappearing on timescales from hours to weeks. Monitoring current solar activity helps me decide when it's worth the effort to set up an image and what features I should focus on capturing. Several excellent resources provide real-time information about solar activity. The Solar Dynamics Observatory, or SDO, operated by NASA, has multiple instruments continuously imaging the sun in various wavelengths, and these images are available online with only a few hours delay. The GONG Network, Global Oscillation Network Group, maintains a network of ground-based solar telescopes around the world, providing continuous H-alpha images. The SOHO Satellite, Solar and Heliospheric Observatory, has been watching the sun continuously since 1996 and provides images in multiple wavelengths. These professional observations help me identify when interesting features are present on the visible solar disk. What am I looking for when I check these solar monitoring resources? Large sunspot groups are always exciting to image, especially when they have complex magnetic structures that might produce flares. Active regions with significant H-alpha features like filaments and plagers indicate areas where interesting dynamics might be occurring. Prominences visible around the solar limb, particularly large or unusually shaped ones, are prime targets for H-alpha imaging. When space weather monitoring sites report increased solar activity, solar flares, or coronal mass ejections, I make an extra effort to get out an image because these events often produce dramatic, visible features. I also pay attention to the solar rotation, which has a period of about 27 days, as seen from Earth, when an interesting active region first appears around the eastern limb of the sun. I know I'll have roughly 2 weeks to image it as it transits across the visible face of the sun before it rotates out of view on the western limb. Beyond atmospheric and solar conditions. Practical considerations also factor into my planning. I need clear skies, obviously. But for solar imaging, I can work with conditions that wouldn't be suitable for nighttime astronomy. Thin clouds or haze that would ruin a nighttime imaging session might still allow solar imaging, though the images won't be quite as sharp and contrasty. I need to make sure I have time available. On the morning of an imaging session, I typically start my setup about an hour before I plan to begin capturing images. This gives me time to get everything assembled and aligned properly, while atmospheric conditions are still improving, and it allows my equipment to thermally stabilize at outdoor temperature, which is important for maintaining focus. Let me walk you through my complete setup process step by step, explaining not just what I do but why each step matters for achieving the best possible results. I begin by selecting my imaging location carefully. My ideal spot is a grassy area in my backyard that has a clear view of the eastern sky for morning imaging sessions. Minimal obstruction from trees or buildings that might cast moving shadows as the sun rises higher, and protection from wind that could shake my equipment. The grass provides better seeing than imaging over pavement or concrete, and the relatively clear horizon allows me to start imaging as soon as possible after sunrise when seeing conditions are often at their best. I set up my equipment on a solid, level surface, using either a concrete pad or a sturdy table, because any vibration or instability in the base will translate directly into shake in my images. Some images use tripods, which offer portability and ease of setup, but I prefer a more solid mounting solution when possible because it provides better vibration damping. Next, I set up my equatorial mount and carefully level and align it. An equatorial mount is a special type of telescope mount that's designed to track the apparent motion of celestial objects as Earth rotates. Unlike a simple alt-azimuth mount that moves up, down, and left-right, an equatorial mount has one axis, called the polar axis or right ascension axis, aligned parallel to Earth's axis of rotation. When this axis is properly aligned, a simple rotation around that axis at a constant rate compensates perfectly for Earth's rotation and keeps celestial objects centered in your telescope's field of view. Getting this polar alignment correct is crucial for solar imaging, because even though the sun moves slowly across the sky to the naked eye, at the high magnifications used in solar imaging, improper tracking will cause the sun to drift out of your field of view within minutes. For polar alignment, I use a technique that involves pointing the mount's polar axis toward the celestial North Pole. In the northern hemisphere, the star Polaris is very close to the celestial pole, making alignment relatively straightforward at night. But during the day, I can't see Polaris. Instead, I use an alignment method based on my locations, latitude, and my mount's built-in compass and level indicators. I set the mount's latitude adjustment to match my precise latitude, which I've determined using GPS coordinates from my imaging location, and I use a compass to orient the mount's base, so the polar axis points north. This gets me close enough for solar imaging, though not as precise as a nighttime polar alignment using Polaris. Some advanced imagers use specialized solar polar alignment techniques, but for most purposes, a rough daylight alignment is sufficient because we're typically imaging for relatively short periods and can make minor tracking corrections if needed. With the mount set up and aligned, I carefully attach my telescope to the mount's saddle plate, making sure all attachment bolts are secure and the telescope is balanced both in right ascension and decline. Proper balance is important because it reduces the strain on the mount's motors, allows for smoother tracking, and minimizes the chance of the telescope shifting unexpectedly and potentially causing the solar filter to become misaligned. To balance the telescope, I position it horizontally and adjust its position in the mounting rings or saddle until it remains level when I release it, neither falling forward nor backward. I repeat this process with the telescope pointed in different directions to verify balance across the full range of motion I'll be using. Now comes the critical safety step: attaching the solar filter. Before I even think about pointing the telescope toward the sun, I must ensure the solar filter is properly and securely attached to the front of the telescope. I inspect my solar filter carefully, holding it up to a bright light and looking for any pinholes, tears, or damage to the filter material. Even a tiny defect could allow dangerous levels of sunlight through and damage my camera or eyes. Finding the filter in perfect condition, I attach it to the telescope's dew shield or front aperture ring. making sure it's seated securely and cannot fall off or be blown off by wind. Many filter cells use tension rings or elastic bands to hold the filter in place. I double-check these and give the filter a gentle tug to verify it's secure. Only after confirming the filter is properly attached and completely covering the telescope's aperture do I allow the telescope to be pointed anywhere. Near the sun, I connect my astronomy camera to the telescope's focuser, securing it firmly so there's no chance of it coming loose during the imaging session. The camera connects to my laptop via a USB cable, which I route carefully to avoid putting strain on the camera's USB port or creating a trip hazard. I power up my laptop, which I've placed on a small table near my telescope where I can see the screen even in bright daylight, and I launch my imaging software. The software I use is called Fire Capture, which is specifically designed for planetary and solar imaging. It provides a live preview of the camera's view, extensive control over camera settings like exposure, time, gain, and region of interest, tools for focusing and alignment, and the ability to record high frame rate video directly to my laptop's hard drive. There are other excellent options including SharpCap and AstroDMX Capture, all offering similar features with slightly different interfaces and capabilities, with all the hardware connected and software running. I'm almost ready to point the telescope at the sun, but first I do one final safety check. I verify once more that the solar filter is securely attached. I confirm that the camera is properly connected and not showing any errors. I check that my laptop has plenty of battery life and storage space available, and I make sure there are no people or pets nearby who might accidentally look through the findoscope or touch the equipment. Only when I'm completely satisfied that everything is safe and ready, do I begin the process of pointing the telescope toward the sun. Pointing the telescope at the sun might sound trivial. After all, it's the brightest object in the sky and impossible to miss, but doing it safely and precisely requires a careful technique. I never, under any circumstances, look through the telescope's findoscope or eyepiece when searching for the sun, even with the solar filter in place on the main telescope. Findoscopes typically don't have their own filters, and looking through them would expose my eyes to the full, unfiltered intensity of the sun. Some images cover their findoscopes, or remove them entirely during solar imaging sessions to eliminate any temptation or accidental viewing. Instead of using the findoscope, I use the shadow projection method to roughly align the telescope. The shadow projection method is simple, but effective. I position myself so I can see the shadow cast by the telescope on the ground, and I slowly slew the telescope mount, watching the shadow change shape. When the telescope is pointed directly at the sun, it casts the smallest possible shadow because the telescope tube is perfectly aligned with the light from the sun. As the telescope gets closer to solar alignment, I can see the shadow shrinking. And when I'm very close, I can see the circular shadow of the telescope's front aperture becoming more defined and symmetrical. Once the shadow is minimized, I'm close enough that I can check my laptop screen to see if the sun is visible in the camera's field of view. Usually, the sun appears somewhere in the frame, perhaps not perfectly centered, but visible enough that I can use the mouse controls to bring it to the center of the frame. Seeing the sun appear on my laptop screen for the first time in each imaging session never gets old. Even though I've done this hundreds of times, there's still a thrill when that bright disk suddenly appears, filtered and safe but revealing detail that's invisible to the naked eye. The first thing I notice is whether there are sunspots visible. If I've checked solar monitoring sites, I already know approximately what to expect. But seeing it directly through my own equipment is always more exciting. On days with high solar activity during solar maximum, the solar disk might be peppered with multiple sunspot groups, dark blemishes of various sizes scattered across the bright photosphere. On quiet days near solar minimum, the disk might be completely blank, showing only the subtle granulation texture of the solar surface. Before I can capture any useful images, I need to achieve accurate focus. And this is where the real challenge begins. Focusing on the sun at high magnification is difficult because of atmospheric turbulence, constantly changing the apparent sharpness of the image, and because the depth of focus at these magnifications is incredibly shallow. When I first point the telescope at the sun, the image is typically quite blurry, showing the solar disk but without any fine detail visible. Using Fire Capture's focus aid tools, which provide numerical measurements of image contrast and sharpness, I begin slowly adjusting my telescope's electronic focuser. I make small movements, just a few steps at a time, and watch both the live image and the focus metrics, trying to find that sweet spot where everything snaps into perfect clarity. Atmospheric turbulence makes this process frustrating at times. Just when I think I've achieved good focus, a wave of turbulent air passes through, and the image becomes a blurry mess. making me question whether I actually had good focus, or whether I need to adjust further. This is where experience and patience come into play. I've learned to wait for brief moments of seeing stability, when the atmosphere calms down momentarily and the image suddenly becomes sharp. During these moments, which might last only a second or two, I can judge whether my focus is truly optimal. If I see sharp granulation appearing across the solar surface during these moments of good seeing, I know I'm close to perfect focus. If the image is still somewhat soft, even during moments of good seeing, I need to adjust the focus further. I spend typically 10 to 15 minutes on initial focusing, and I return to check and refine focus periodically throughout the imaging session because temperature changes can cause focus to drift. The metal components of the telescope expand or contract slightly as the temperature changes, which shifts the focal point. On a cool morning that's warming up quickly, I might need to refocus every 20 to 30 minutes to maintain optimal sharpness. Some electronic focusers have temperature compensation features that automatically adjust focus as temperature changes. But I prefer to check manually because I want to be absolutely certain I'm maintaining the best possible focus for each recording. Once I achieve good focus and have the sun centered in my frame, I'm ready to start capturing data. But before I do, I take a moment to adjust my camera settings to optimize them for the current conditions. The exposure time needs to be short enough that the sun doesn't appear overexposed, but long enough that I'm getting good signal-to-noise ratio in the darker areas like sunspot umbra. The gain setting on my camera, which is similar to ISO in traditional photography, needs to be set high enough that I'm using the full range of the camera's analog-to-digital converter, but not so high that I'm introducing excessive noise. I typically start with conservative settings and then adjust based on what I'm seeing in the live preview and histogram. For white light imaging, I'm usually shooting at exposures between 1 and 5 milliseconds, with gain settings that result in the brightest parts of the solar disk being at about 70 to 80% of maximum brightness, leaving some headroom to avoid clipping highlights. With my equipment set up, focused, and optimized, I'm finally ready to start recording the actual data that will become my final images. This is where the hours of preparation and careful setup pay off, and where the magic of modern solar imaging really happens. Instead of taking single photographs, like traditional photography, I'm going to record high-speed video of the sun, capturing thousands of individual frames that will later be analyzed and combined during post-processing. Let me explain exactly how this works and why it's such a powerful technique. The fundamental concept behind Lutfi imaging is that atmospheric turbulence is random and constantly changing. At any given instant, different parts of my optical path from the sun through Earth's atmosphere to my telescope are experiencing different levels of turbulence. Some portions of the path might be going through relatively calm, stable air, while other portions are going through turbulent, churning air masses. This creates a constantly shifting pattern of distortion across the solar image. If I were to take just one photograph, I would capture whatever random atmospheric condition happened to exist at that specific instant. And that photograph might be quite blurry if I happen to catch a moment of poor seeing. But if I record hundreds or thousands of frames in rapid succession, I'm essentially sampling the atmospheric conditions many times. And statistics tells us that some of those frames will have been captured during brief moments when the atmosphere was particularly calm and stable. I set my camera to record at its maximum frame rate, which for my ZWOAIS 178mm is about 160 frames per second when using the full sensor. Or even faster, if I crop down to a smaller region of interest, around a particularly active area. Higher frame rates mean I'm capturing more samples of the atmospheric conditions, increasing my chances of recording frames during those precious moments of excellent seeing. Each recording session typically lasts between 30 seconds and 2 minutes. This duration gives me enough frames to work with during processing, typically 4,000 to 20,000 frames depending on frame rate, while not creating video files that are so large they become unwieldy to process. I don't just randomly record for 2 minutes and hope for the best. Instead, I watch the live preview carefully, waiting for the atmospheric conditions to improve. Seeing comes in waves. There will be periods of several seconds or even minutes where the image is constantly boiling and blurry. And then suddenly the atmosphere will calm down briefly and details will snap into sharp focus. When I see these moments of improved seeing starting to occur, that's when I start my recording. By timing my recordings to coincide with periods of better seeing, I dramatically increase the percentage of sharp frames in my video files, which means better final images after processing. I capture multiple recordings of the same area from slightly different perspectives, or at different times to increase my dataset and improve my chances of capturing the best possible seeing. If there's a particularly interesting sunspot group, I might record 10 or 15 separate video files of that region over the course of an hour, each time waiting for moments of good seeing before starting the recording. This might seem redundant, but atmospheric conditions change, and what looked like the best possible focus and sharpness 20 minutes ago might be surpassed by even better conditions later. Having multiple recordings to choose from gives me options during processing. I also capture full disk overview images in addition to my high-resolution close-ups of specific regions. For full disk imaging, I typically use a Barlow lens or field flattener to reduce magnification and fit the entire solar disk in my camera's field of view. These full disk images provide context, showing the overall distribution and location of sunspots and active regions, and they're useful for creating animated sequences showing solar rotation over multiple days or weeks. The imaging technique for full disk is similar to close-up imaging, recording high-speed video and applying lucky imaging techniques. But the seeing requirements are less critical because you're not trying to resolve fine details at extreme magnification. If I'm doing H-alpha imaging, my approach is slightly different because H-alpha features like prominences are often most dramatic right at the solar limb, the edge of the sun's visible disk. To capture these prominences, I need to carefully position the sun so the limb is just inside my field of view, revealing the prominences extending beyond the edge into space. This requires precise positioning and tracking because any drift in the telescope's tracking will cause the prominences to move out of frame. Prominences can change surprisingly quickly, growing, shifting, erupting, or fading over the course of minutes to hours. So when I observe particularly active or dramatic prominence, I try to capture it multiple times throughout the session to document its evolution. Prominences can change surprisingly quickly, growing, shifting, erupting, or fading over the course of minutes to hours. So when I observe particularly active or dramatic prominence, I try to capture it multiple times throughout the session to document its evolution throughout the entire imaging session, which typically lasts 2 to 4 hours. I'm constantly monitoring several factors. I watch the live image quality, checking whether focus is remaining sharp or drifting due to temperature changes. I monitor seeing conditions, noting when good seeing periods occur and timing my recordings accordingly. I check that my equipment is tracking properly and the sun is staying centered in my field of view. I verify that my laptop has sufficient storage space and isn't having any performance issues that might cause frame drops in the recordings. And I enjoy the experience, taking moments to simply observe the sun in real time, watching granules moving and shifting, seeing sunspots evolving, noting any flares or brightening in active regions. This direct connection to observing our nearest star, seeing it as a dynamic living object rather than just a static yellow circle in the sky, is one of the great joys of solar imaging. After completing my imaging session and packing up my equipment, I'm left with gigabytes of video files containing tens or hundreds of thousands of individual frames of the sun. These raw videos, while they captured the data I need, are not yet presentable images. The individual frames are relatively low quality, affected by atmospheric turbulence, potentially slightly out of perfect focus, and lacking the contrast and sharpness that bring out fine solar details. The transformation from these raw video files into stunning final images happens during post-processing. And this is where dedicated software and carefully refined techniques turned good data into great images. Let me walk you through my entire processing workflow step by step. The first stage of processing is called frame selection and stacking, and this is where the lucky imaging concept comes into full effect. I use software called AutoStacker, which is specifically designed for planetary and solar image stacking. I load my video file into AutoStacker, which analyzes every single frame, assigning each frame a quality score based on measurements of contrast and sharpness. The software is looking for frames where atmospheric turbulence happen to be minimal, where details are sharp and well-defined rather than blurred and distorted. After analyzing all the frames, AutoStacker ranks them from best to worst quality. I then select a percentage of the best frames to stack together, typically the top 5 to 10%, though sometimes I'll use as few as the best 1% if seeing conditions were particularly variable. If I recorded 5,000 frames and I'm keeping the best 5%, that means I'm stacking the top 250 frames. Stacking these frames involves several sophisticated steps. First, the software must precisely align all the selected frames so features are in exactly the same pixel positions across all frames. This alignment is necessary because even with a tracking map, there's always tiny amounts of drift, vibration, or atmospheric refraction causing slight shifts in the sun's position from frame to frame. AutoStacker uses reference points across the solar disk to calculate these shifts and computationally align all the frames to subpixel accuracy. Once aligned, the frames are combined by averaging them together, pixel by pixel. This averaging process has several beneficial effects. Random noise, which varies from frame to frame, gets averaged out and reduced significantly. Atmospheric distortions, which are different in each frame, partially cancel out. And the true solar features, which are consistent across all frames, are reinforced and become clearer. The improvement from stacking is often dramatic and gratifying. A single frame from the video might show only hints of granulation and modest detail in sunspot structure. The stacked image reveals sharp granulation across the entire solar surface, intricate penumbral structure in sunspots, bright facular and plonges around active regions, and a level of detail that simply isn't visible in any individual frame. This is the power of lucky imaging combined with sophisticated image stacking. We've effectively used our large sample of frames to extract the best possible image from moments when atmospheric conditions were optimal. After stacking, the image is sharper and cleaner than any individual frame, but is still not as sharp or detailed as it could be. This is where the second major processing stage comes in, wavelet sharpening. Wavelets are a mathematical technique from signal processing that allows us to decompose an image into different spatial frequency layers, essentially separating out features at different size scales. At the largest scales, we have the overall shape and brightness of the solar disk. At intermediate scales, we have sunspot groups and large-scale features. At smaller scales, we have individual granules and fine penumbral structure. At the finest scales, we have tiny details and small-scale brightness variations. I use a program called Registax for wavelet processing. I load my stacked image from AutoStacker and open the wavelet panel, which presents me with several wavelet layer sliders corresponding to different size scales. By adjusting these sliders, I can selectively enhance details at each scale. For solar imaging, I typically emphasize the finest layers to bring out granulation detail and subtle structure, while being more conservative with the larger scale layers to avoid creating artificial-looking contrast. The key is finding a balance where the image looks natural, but shows all the detail that's truly present in the data. It's easy to overprocess and create an image that looks unnaturally sharp or contrasty. So I frequently zoom out and view the full image to make sure I'm not pushing the processing too far. After wavelet sharpening, I export the image from Resolve and bring it into Adobe Photoshop for final refinement. In Photoshop, I adjust the overall brightness and contrast curves to optimize the tonal range. I want the bright photosphere to show subtle variations without being blown out to pure white. And I want the darker sunspot ombre to show structure and detail without being crushed to pure black. I use selective adjustments to bring out detail in areas of particular interest, perhaps increasing contrast slightly in a sunspot group to emphasize its magnetic structure. I apply careful noise reduction to smooth out any remaining grain from the imaging process, using techniques that preserve edge detail while cleaning up smooth areas. I might apply slight color corrections if I'm working with color images, ensuring that the sun has a pleasing and natural appearance. For images that span a large brightness range, like a Chalfak images that show both bright prominences and subtle surface features, I sometimes use HDR techniques, combining multiple processed versions of the same stacked image with different tonal ranges to create a final image that shows detail across the entire brightness range. This requires careful blending to avoid creating obvious halos or unnatural-looking transitions between different exposure levels. The final step in my processing workflow is adding annotations and context. I create a clean black border around the solar disk to provide a professional presentation. I add text indicating the date, time, and equipment used for the image, providing important context for viewers and creating a historical record of when features were observed. If the image shows particularly interesting features like a large sunspot group, I might add labels identifying them. For full disk images, I sometimes add north-south orientation, indicators and scale information showing the size of features in kilometers. The entire processing workflow, from importing the raw video file to exporting the final polished image, typically takes me 30 minutes to an hour per video file, depending on the size of the data and how much refinement the image needs. For a single imaging session where I captured 10 to 20 video files, this means I might spend 6 to 10 hours on post-processing, spread out over several days. Some people might find this tedious, but I find it meditative and satisfying, gradually coaxing out the details that were hidden in the raw data. Watching an image transform from a soft preliminary stack into a sharp, detailed final result that reveals the intricate structure of our nearest star dot. After all the planning, setup, imaging, and processing, The moment of truth arrives when I view the final processed image and see what I was able to capture. Every imaging session produces unique results because the sun is constantly changing. And this unpredictability is part of what makes solar imaging so endlessly fascinating. Let me describe some of the incredible features and phenomena that become visible through dedicated solar imaging, and what they reveal about the nature of our star. The most immediately striking feature in white light solar images is sunspots. Those dark blemishes that appear scattered across the bright solar surface. Sunspots have fascinated humans since ancient times, with historical records of naked eye sunspot observations going back thousands of years in China and other cultures. Though it wasn't until Galileo's telescopic observations in the early 600s that their true nature began to be understood. We now know that sunspots are regions where intense magnetic fields, thousands of times stronger than Earth's magnetic field, break through the solar surface and suppress the normal convective flow of heat from the sun's interior. This makes sunspots cooler than the surrounding photosphere, typically around 4,000 degrees Celsius compared to 5,500 degrees for the normal photosphere. And this temperature difference makes them appear darker even though they're still incredibly hot and would glow brightly if you could see them against a dark background. A well-developed sunspot reveals intricate structure when imaged at high resolution. The darker central region is called the umbra, where the magnetic field is strongest and heat flow is most suppressed. Surrounding the umbra is the penumbra, a lighter gray region showing an incredible radial filamentary structure, like tiny threads or fibrils radiating outward from the umbra. These penumbral filaments are related to the geometry of the magnetic field, and they show the direction that plasma is flowing along magnetic field lines. In the most detailed images captured during excellent seeing, you can see individual filaments, bright dots called penumbral grains, moving along the filaments, and bright structures called light bridges that sometimes cut across the umbra, all revealing the complex magnetic and convective processes occurring in and around sunspots. Beyond the sunspot itself, the area surrounding active regions shows additional fascinating features. Facula are bright patches that appear near sunspots and around the edges of active regions. They're regions where magnetic fields are vertical rather than horizontal, allowing more heat to reach the surface and making them appear brighter than normal photosphere. Near the solar limb, the edge of the visible disk facula become more prominent due to a projection effect, and they can create beautiful bright patches contrasting with the darker edge of the solar disk. Plushes, which are similar to faculae, but visible primarily in certain wavelengths, like calcium K or H-alpha, surround active regions and indicate areas of concentrated magnetic field that are often associated with solar flare activity. Covering the entire solar surface is granulation, the convection pattern created by hot plasma rising from the sun's interior, reaching the surface, cooling slightly, and sinking back down. Each granule is a convection cell, bright in the center where hot plasma is rising, darker around the edges where cooled plasma is sinking. The granules are constantly changing, with a typical lifetime of about 8 to 20 minutes. So the solar surface is never static, but always boiling and churning. The scale of this granulation is mind-boggling. Each granule is about 1,000 kilometers across, roughly the size of Texas, which means that in a high-resolution image of the sun, you're seeing thousands of individual granules, each one large enough to swallow Earth multiple times over. Surrounding the granules is the photospheric network, a lace-like pattern of bright lanes where magnetic fields are concentrated, creating a cobweb-like structure across the entire solar surface. When imaging in H-alpha, an entirely different view of the sun emerges. The most dramatic features visible in H-alpha are prominences, enormous structures of relatively cool plasma suspended in the sun's hot corona by magnetic field loops. Prominences extend above the solar surface, sometimes reaching heights of several 100,000 kilometers, which is a significant fraction of the sun's radius. They appear as bright arches, loops, or curtain-like structures when seen against the darkness of space beyond the solar limb, and they're absolutely spectacular to observe. Some prominences are quiescent, remaining stable for days or weeks, slowly evolving and changing shape. Others are eruptive, rapidly rising and expanding over the course of hours as they are flung away from the sun by magnetic instabilities, sometimes becoming part of coronal mass ejections that hurtle through space toward Earth. On the solar disk itself, H-alpha imaging reveals filaments, which are prominences seen from above rather than from the side. They appear as dark, snake-like features threading across the bright H-alpha disk, marking the locations of magnetic field structures. Active regions show bright plonges, and dark fibrils radiating away from sunspot groups. When solar flares occur, they appear as sudden brightenings in H-alpha active regions, sometimes so bright that they're visible even through the camera as a flash. I've been fortunate to capture several flares in progress, and it's an incredible experience to watch that sudden brightening, knowing that you're witnessing the release of energy equivalent to billions of nuclear bombs, an explosion so powerful that the X-rays and high-energy particles it produces can affect Earth's ionosphere and create radio blackouts here on our planet. The images I've captured over years of solar imaging have given me an intimate familiarity with our star that would have been impossible to gain any other way. I've watched sunspot groups appear, grow, develop complex magnetic structures, produce efflares, and then gradually decay and disappear as they rotate across the solar disk. I've seen prominences rise from the limb, hang suspended for days, and then either erupt spectacularly or gently fall back to the surface. I've documented the progression of solar cycle 25 from its quiet beginnings through its current approach to solar maximum, watching the number and complexity of sunspots increase year by year. I've contributed my observations to scientific databases where they're used by professional researchers studying solar activity and space weather, and I've shared my images with others through social media, astronomy forums, and presentations, helping people understand that the sun is not just a lifeless ball of gas, but a dynamic, living system that affects our lives here on Earth in profound ways every single day. As I conclude this comprehensive guide to solar imaging, I want to emphasize that while the technical aspects might seem daunting at first, anyone with dedication and patience can learn these skills and capture their own incredible images of the sun. Start simple with basic equipment, learn the fundamentals of safety, focus, and atmospheric seeing. Practice regularly to develop your skills, and gradually upgrade your equipment as you discover what aspects of solar imaging excite you most. The sun is always there, offering new features to observe and capture. And the sense of accomplishment from capturing detailed solar images with your own equipment is absolutely worth the effort. Whether you're fascinated by the physics of sunspots and magnetic fields, drawn to the aesthetic beauty of prominences in solar structure, interested in contributing to solar monitoring and citizen science, or simply looking for a challenging and rewarding form of astrophotography, solar imaging offers endless opportunities for exploration and discovery. Our nearest star awaits your camera, ready to reveal its secrets to anyone willing to point their lens toward the day sky with proper filters, patience, and passion.
Through quantum tunneling, each baby universe has slightly different physical constants. Over many generations, this process selects for universes optimized to produce black holes, which also happen to be good at producing stars, planets, and complexity. We exist in such a universe not by chance, but because only this type of universe can persist through the selection process. The universe bootstraps its own existence through an evolutionary mechanism spanning across cosmic generations. These ideas remain controversial and difficult to test, but they point toward a resolution of the deepest mystery. Why is there something rather than nothing? The answer might be that nothing is unstable in a quantum framework. Any fluctuation that creates something which can sustain itself will persist. Others collapse. We observe a self-sustaining arrangement because non-sustaining ones don't produce observers. The universe exists because it can exist. The conditions making it possible are the conditions it selects for through its own evolution. Reality is a strange loop that creates itself, and the mathematics describing this gets even stranger. We experience 3 dimensions of space: left-right, forward-backward, up-down. Add time and you get 4 dimensions. String theory says there are at least 7 more hidden dimensions, giving a total of 11. Why haven't we noticed them? The theory proposes they're compactified, curled up so tiny that we can't perceive them. Imagine an ant walking on a telephone wire. From far away, the wire looks one-dimensional. The ant can only move forward or backward. But up close, the wire has thickness. The ant could walk around its circumference, exploring a second dimension we initially missed. The extra dimensions in string theory work similarly. They exist at every point in our 3-dimensional space, but they're rolled up at scales far smaller than atoms, Particles can vibrate through these hidden dimensions, and different vibration patterns appear to us as different particle types. An electron is one vibration mode, a quark is another. Photons, neutrinos, everything emerges from strings vibrating through this higher dimensional space. This framework has profound implications for cosmology. Our universe might be a three-dimensional surface embedded in this higher dimensional space. Everything we see, stars, galaxies, light, is trapped on this surface. But gravity is different. Gravitational effects can leak into the extra dimensions, which might explain why gravity is so much weaker than the other fundamental forces. The ekpyrotic model we discussed earlier exploits this. If parallel three-dimensional branes exist in the higher dimensional bulk, and if they can move through those extra dimensions, then collisions become possible. Our bang would be the aftermath of such a collision, with the pre-collision state existing in this higher dimensional framework. String theory also suggests that different compactifications of the extra dimensions produce different physical laws. There might be 10 to the 500th or more distinct ways to curl up the extra dimensions, each creating a different vacuum state with different particle masses and force strengths. This vast landscape of possibilities connects to the idea of varying constants between cosmic cycles. Testing these ideas is extraordinarily difficult. The energies needed to probe the extra dimensions directly exceed anything achievable in particle accelerators by many orders of magnitude. But indirect evidence might exist. Gravitational waves propagating through the bulk could carry signatures of extra dimensions. Tiny deviations in how gravity behaves at small scales might reveal the geometry of hidden dimensions. Experiments at the Large Hadron Collider searched for signs of extra dimensions by looking for missing energy in particle collisions. If particles escaped into the bulk, energy would seem to disappear. So far, no definitive signals, but the search continues at higher energies and with greater precision. String theory remains incomplete and controversial. Some physicists embrace it as the best candidate for a theory of everything. Others criticize it for making few testable predictions and requiring fine-tuning to match observations. The debate continues, but the core insight persists. The universe we observe might be a shadow of a larger reality. The three dimensions of space we navigate might be an illusion, a projection of something far more complex existing in realms we can't directly access. This raises a question about the pre-bang state. If extra dimensions exist, what role do they play in the universe's origin? Inflation was supposed to be a one-time event, a brief phase of exponential expansion that set up our bang, then ended. But the mathematics suggests something far stranger. Once inflation starts, it might never completely stop. Here's why. Inflation is driven by a quantum field called the inflaton. When this field sits at a high energy value, space expands exponentially. As the field rolls down toward lower energy, inflation slows and eventually stops. The field's energy converts to matter and radiation. That's the bang we know. But quantum changes affect the inflaton field just like they affect everything else. In some regions of space, random changes push the field back up to higher energy before it can finish rolling down. Those regions keep inflating. Meanwhile, other regions successfully end inflation and produce hot bang conditions. This creates a fractal structure. Our observable universe is a pocket where inflation ended. But beyond our cosmic horizon, other regions are still inflating. And within those inflating regions, new pockets constantly form where inflation stops. Each pocket becomes a bang universe. Each one expands, cools, and potentially develops galaxies, stars, and life. The process never ends. Alan Guth and André Linde developed this eternal inflation framework in the 1980s. It's a natural consequence of combining inflation with quantum mechanics. The implications are staggering. There's not one universe. There's a vast, possibly infinite multiverse. Our bang is just one bubble in an endless foam of universes. Each bubble might have different properties. The quantum changes creating new pockets could also affect the values of physical constants, producing pocket universes with different physical laws. This solves some mysteries while creating others. It explains why our universe has life-permitting constants. There are infinite universes with all possible constants. We necessarily find ourselves in one compatible with our existence. But it also means the theory can't predict what we should see, because every possible observation occurs somewhere in the multiverse. Eternal inflation also has a past. The Border-Guth-Vilenkin theorem, proved in 2003, shows that any region of space expanding on average must have a boundary in the past. Inflation can't be eternal into the past. It must have started somehow, from some initial state. This brings us back to the origin question. What triggered inflation in the first place? The metastable false vacuum? A quantum change? A prior contracting phase? The theorem doesn't tell us what came beforehand, but it proves there was a beforehand. Some physicists find eternal inflation disturbing. It seems to make science impossible if every outcome exists somewhere. Others argue we can still make probabilistic predictions by counting which types of observers are most common across the multiverse. The debate is unresolved, but the math of eternal inflation is solid. Unless quantum mechanics or the inflaton field behaves very differently than we think, the multiverse seems unavoidable. What does this mean for the concept of nothingness? Stand back and look at the big picture. If eternal inflation is correct, reality is not a single universe with one bang. It's an infinite collection of disconnected regions, each with its own bang, expanding within an ever-inflating background. Think of it as quantum foam on a cosmic scale. The inflating space is the substance. The pocket universes are bubbles forming within it. Each bubble thinks it's the entire universe because the inflating background expands faster than light, forever hiding other bubbles beyond an unreachable horizon. This structure might be nested. Within each pocket universe, if conditions allow, new phases of inflation could start. Those would spawn their own sub-pockets. You'd get a hierarchy of nested realities, each level spawning the next, all embedded within the eternal inflation that never stops. Max Tegmark has classified different types of multiverses. Level 1 is simply distant regions of our own universe beyond our observation horizon, but obeying the same physics. Level 2 is the eternal inflation multiverse we're discussing. Different bubbles with potentially different physical constants. Level 3 involves the many worlds interpretation of quantum mechanics, where every quantum measurement splits reality into branches. Level 4 would be completely different mathematical structures obeying different logical rules. The Level 2 multiverse from eternal inflation is the most scientifically grounded. It emerges directly from combining well-tested physics, general relativity, quantum mechanics, and inflation. You don't need to assume anything exotic. The multiverse is a consequence, not an assumption, but it creates an observability problem. We can only see inside our bubble. The inflating background between bubbles expands so rapidly that light from other bubbles can never reach us. They're not just far away, they're causally disconnected. No information can travel between bubbles. Each pocket universe is fundamentally isolated. This seems to put other bubbles beyond science's reach. If we can't observe them, test predictions about them, or interact with them in any way, are they really scientific entities, or have we crossed into metaphysics? Some argue the multiverse remains scientific because it's a prediction of testable theories. We don't test the multiverse directly, we test inflation. If inflation is correct, eternal inflation follows naturally. Rejecting the multiverse means rejecting the logical consequences of confirmed physics. Others remain skeptical. They argue that good scientific theory should make definite predictions about what we see. The multiverse allows anything, which means it predicts nothing. It's a failure of our theories, not a feature of reality. The debate continues, but observationally we're stuck in our bubble. We can study its properties. We can map the cosmic microwave background. We can measure the expansion rate and the dark energy density. All of this tells us about our pocket universe. Whether infinite other pockets exist remains unknown, but the math strongly suggests they do. And if they do, then the question of what existed before our bang gets even stranger. Our bang was not the start of inflation. It was the end of inflation in our local region. Other regions never stopped inflating. Still others ended inflation earlier or later. There's no universal before the bang. Each pocket has its own timeline, its own origin, its own history. The multiverse as a whole might be timeless, with pockets starting and ending at all moments, embedded in an eternal background. This is the picture modern cosmology paints. Not a simple creation story, a complex layered reality where our universe is one small piece. For decades, popular science treated the Bang singularity as a physical reality, a point where the universe was infinitely dense, infinitely hot, infinitely curved. But physicists never believed it. A singularity signals the breakdown of your theory, not a description of reality. When equations give infinite answers, they're telling you the mathematical framework no longer applies. You've pushed the model beyond its domain of validity. General relativity predicts singularities. Black holes have them at their centers. Our bang has one at its start. But general relativity is a classical theory. It doesn't include quantum mechanics. At small scales and high energies, quantum effects become crucial. Ignoring them guarantees your prediction will fail. Think of it like predicting the behavior of water. Classical fluid mechanics works great for describing rivers, waves, and pipes. But at molecular scales where individual water molecules matter, you need quantum chemistry. Classical fluid equations give nonsensical results at atomic scales because they're the wrong tool. General relativity is the wrong tool at Planck scales. The Planck length is 10 to the negative 35 meters. The Planck time is 10 to the negative 43 seconds. The Planck energy is about 10 to the 19 Geiger electron volts, roughly the energy of a flying mosquito compressed into a single particle. These are the scales where quantum gravity becomes essential. At these scales, space and time stop behaving classically. They fluctuate. They become uncertain. The very concepts of distance and duration lose their usual meanings. A singularity, which requires compressing something into exactly zero volume, becomes impossible. Quantum mechanics won't allow it. Stephen Hawking and Roger Penrose proved theorems showing that general relativity predicts singularities under very general conditions. Their work was brilliant and crucial, but it also highlighted exactly where general relativity fails. The singularity theorems tell us where we need a better theory. Loop quantum gravity replaces the singularity with a bounce. String theory might replace it with a minimum size determined by string length scales. Other quantum gravity proposals have their own solutions. The details differ, but the conclusion is the same. The singularity isn't real. This means our bang wasn't a moment when the universe sprang from nothing into something. It was a transition from one quantum state to another. The pre-transition state might have been a contracting universe, an inflating vacuum, a higher dimensional brain arrangement, or something else entirely. But it was something, not nothing. The mathematical fiction of the singularity misled generations of physicists and the public. It made the universe's origin seem more mysterious than it is. Yes, we don't fully understand quantum gravity. Yes, the precise details of the transition remain unclear. But we know the universe didn't start at an infinitely dense point because infinite density is unphysical. This shifts the question. We're not trying to explain how something came from absolute nothing. We're trying to explain what the pre-bang quantum state was and why it transitioned into our current expanding universe. That's still a profound question, but it's a tractable one. Quantum mechanics and general relativity are both experimentally validated to incredible precision. Quantum mechanics predicts the behavior of atoms, lasers, and computer chips with perfect accuracy. General relativity predicts the orbits of planets, the bending of light around galaxies, and the detection of gravitational waves. Both theories work flawlessly in their domains, but they contradict each other when you try to combine them. This isn't a minor technical issue, it's a fundamental clash of principles. In quantum mechanics, you can measure a particle's energy with arbitrary precision if you're willing to wait long enough. Time is a background parameter that flows uniformly. In general relativity, time is part of space-time, which curves and warps. Time runs at different rates depending on gravity and motion. There's no universal clock. In quantum mechanics, particles exist in superpositions. An electron can be in multiple locations at once until you measure it. In general relativity, space-time has a definite geometry. You can't have space-time in a superposition of different curvatures. Or can you? These contradictions become critical at Planck scales, where both quantum effects and gravitational effects are strong. You need a theory of quantum gravity, a theory that incorporates both sets of principles consistently. Nobody has one yet that's complete, tested, and universally accepted. String theory offers one approach. It replaces point particles with vibrating strings. This smooths out the singularities plaguing quantum gravity calculations. The math is elegant, and the theory potentially describes all forces and particles within one framework. But it requires extra dimensions, has many possible solutions, and makes few testable predictions at accessible energies. Loop quantum gravity takes a different route. It quantizes space-time directly, treating it as a network of discrete loops. This avoids singularities and explains how space emerges from quantum building blocks, but it struggles to incorporate matter and forces beyond gravity. Connecting it to particle physics remains challenging. Other approaches exist. Causal dynamical triangulations build space-time from simple geometric pieces and evolve it through quantum rules. Asymptotic safety suggests gravity might remain well behaved at high energies through a special mathematical property. Emergent gravity frameworks propose that space-time isn't fundamental, but emerges from more basic quantum information. Each approach has strengths and weaknesses. Each makes different predictions about Planck-scale physics. And frustratingly, directly testing these predictions is nearly impossible with current technology. The energies are too high. The scales are too small. But cosmology provides an indirect testing ground. The early universe naturally probed Planck-scale physics. If we can decode the messages written in the cosmic microwave background, in the spectrum of gravitational waves, in the distribution of large-scale structure, we might distinguish between competing quantum gravity theories. This is why understanding what happened before our bang matters scientifically. It's not just philosophical curiosity, it's a window into the most fundamental laws of physics. The universe's origin is the one natural laboratory where quantum gravity was fully operational, leaving fingerprints we can potentially read. The battle between quantum mechanics and general relativity will be resolved. When it is, we'll have a complete picture of how space-time and matter operate at all scales. And with it, we'll understand what nothingness really means in the deepest sense. One equation might hold the key. In 1967, John Wheeler and Bryce DeWitt derived an equation attempting to describe the quantum state of the entire universe. It's deceptively simple looking, but it contains profound implications for cosmology and the question of origin. The Wheeler-DeWitt equation treats the universe's geometry and matter content as quantum variables. Just as an electron has a wave function describing its possible positions, the universe has a wave function describing its possible configurations. The equation tells you how this wave function evolves, not in time, but in terms of relationships between different geometries. Here's the strange part. The equation doesn't contain time. There's no variable representing when things happen. Instead, it describes correlations between different aspects of the universe's state. It's sometimes called the equation with no time, and it raises deep questions about whether time is fundamental or emergent. When applied to cosmology, the Wheeler-DeWitt equation allows solutions where a universe tunnels into existence from a state with zero size. This isn't a metaphor, it's a quantum mechanical process, analogous to how particles tunnel through barriers. The universe starts in an arrangement that classically couldn't expand, then quantum tunneling allows it to jump to an arrangement that can. Alexander Vilenkin developed this universe from nothing scenario using the Wheeler-DeWitt equation. In his framework, the nothing is a quantum vacuum state with no classical space-time. The universe tunnels from this state into a small closed space that immediately begins inflating. From our perspective inside the universe, it looks like time starts at the moment of tunneling, but calling it nothing is misleading. The quantum vacuum state exists. It has properties. It's described by mathematical laws. It's not absolute philosophical nothingness. It's the quantum mechanical ground state before classical time emerges. Other solutions to the Wheeler-DeWitt equation exist. The Hartle-Hawking no-boundary proposal uses imaginary time to smooth out the singularity. Bohm's pilot wave interpretation suggests the quantum potential in the equation acts like an effective cosmological constant. Each approach gives different insights into what the pre-classical state might be. Chinese physicists Dongshan He, Dongfang Gao, and Qingyu Kai published work in 2014 exploring spontaneous creation solutions. They showed that under certain conditions, a Planck-sized vacuum bubble has a non-zero quantum probability of expanding rather than collapsing. Once expansion starts, inflation takes over and creates a universe. The probability is tiny. But in a timeless quantum realm where all possibilities exist in superposition, tiny probabilities become actual outcomes given enough trials. And in an eternal quantum foam of fluctuating vacuum states, every possibility eventually happens. This provides a mechanism for the universe's origin that doesn't require an external cause. The quantum vacuum is inherently unstable. Virtual changes constantly occur. Most collapse immediately, but occasionally, by chance, one grows into an inflationary bubble that becomes a universe. The Wheeler-DeWitt equation is not a complete theory. It assumes a particular form of quantum mechanics and doesn't incorporate all aspects of quantum field theory. But it demonstrates that mathematics allows for spontaneous creation of universes from quantum states. Whether nature actually uses this mechanism remains unknown. Testing these ideas is extraordinarily difficult. The wave function of the universe isn't directly observable. We're inside it, part of it. We see its consequences, the structure of space-time, the distribution of matter, but not the underlying quantum state itself. Yet the implications are clear. The universe's origin might be a quantum event requiring no external trigger. The laws of physics themselves might be sufficient to explain existence. Step back from the details and look at the landscape of theories. Inflation before our bang, cyclic bounces, ekpyrotic collisions, eternal inflation multiverse, Wheeler-DeWitt quantum tunneling, loop quantum gravity bridges. Each theory is different, but they share a common theme. None of them require an absolute beginning. Our bang was a transformation, not a creation. Before it came something else, whether inflationary vacuum, contracting universe, quantum foam, or colliding brains. And before that, possibly something else still. The chain of causation might extend infinitely into the past, with no first cause, no moment of creation, no start to time. This challenges our intuition. We're used to stories with beginnings, birth, creation, first moment. But nature doesn't care about human narrative preferences. If the mathematics says time is eternal, then it's eternal. Alternatively, time might be cyclic or even illusory. Roger Penrose's conformal cyclic cosmology suggests the infinite future of one cosmic era becomes the bang of the next. Time loops back on itself. Julian Barber argues time is an emergent property of changing arrangements, not a fundamental dimension. Different perspectives, but both suggest linear time with a definite start is naive. The philosophical implications are profound. If the universe has no beginning, then asking why it exists becomes strange. It exists because it always has existed in some form. Existence is the default state, not something requiring explanation. Nothingness would require explanation. Why wouldn't quantum changes, vacuum energy, or space-time curvature exist? This reverses the usual framing. We've assumed nothingness is simpler than something, so existence needs justification. But in physics, empty quantum states are highly constrained. True nothingness, no fields, no vacuum energy, no quantum changes, no mathematics, no laws, might be impossible. It might violate consistency requirements we don't fully understand yet. If so, then something has always existed and always will exist. The universe transforms continuously. It goes through phases, expanding, contracting, bouncing, inflating, creating structure, dissipating into radiation, repeating. Each phase looks different, but the underlying reality persists. We find ourselves in an expanding phase, seeded by a hot bang that was itself seeded by cold inflation. Trillions of years from now, dark energy might dominate completely, diluting matter to negligible density. The universe would become cold and empty again. Is that an ending, or just another phase transition preparing the conditions for what comes next? If brains collide, another bang could occur. If quantum tunneling happens, new inflationary bubbles could spawn. If loop quantum gravity is correct, maximum density could trigger a bounce. The universe would continue, just in different form. This picture fits with deeper principles in physics. Energy is conserved. Information might be conserved. Fundamental constants seem constant. Reality has structure and follows rules. Why would that structure suddenly appear from nothing or disappear into nothing? The universe doesn't start or end, it transforms. And that transformation is governed by principles we're gradually uncovering through observation, experiment, and mathematical reasoning. The question shifts from, why is there something rather than nothing, to what determines the form that something takes at any given moment? The answer to what existed before our bang is both simpler and stranger than absolute nothing. There was something, a quantum state, a vacuum field, a contracting universe, a colliding brain, a timeless configuration space. The details remain uncertain. The theory differs between frameworks, but the conclusion is consistent. Nothing in the philosophical sense never existed, and possibly cannot exist. The quantum vacuum won't allow it. The uncertainty principle prevents it. The mathematics forbids it. Reality at its deepest level is not empty. It's not static. It's a dynamic system of fields and probabilities and geometry that never stops evolving. Our bang was one moment in this endless evolution. An important moment for us because it created the conditions for stars, planets, and life. But not a special moment cosmically, just a transition, like water becoming steam, except what transitioned was space-time itself. Modern cosmology has pushed our understanding back beyond the traditional bang to reveal a richer story. We know inflation happened first, driven by vacuum energy. We know the universe might be cyclic, bouncing or colliding through endless eras. We know quantum gravity replaces the singularity with something finite. We know the vacuum contains energy shaping cosmic evolution. What we don't know yet is which theory is correct. Is it ekpyrotic collisions, loop quantum bounces, eternal inflation multiverse, quantum tunneling? Perhaps multiple theories are correct in different regimes. Perhaps they're all approximations of a deeper theory we haven't discovered. Future observations will narrow the possibilities. Better measurements of the cosmic microwave background, detection of primordial gravitational waves, more precise tests of dark energy, advances in quantum gravity theories, experiments pushing to higher energies. Each piece of data constrains which models are viable, but already we know enough to revolutionize how we think about creation. The universe didn't come from nothing. It came from something that transforms, that something has always existed, at least as far as our physics can tell. The question isn't why existence rather than non-existence. The question is why this particular form of existence right now, and the answer involves quantum mechanics, gravity, vacuum energy, inflation, and possibly higher dimensions. It involves mathematics describing how fields evolve, how space-time curves, how probabilities collapse into actuality. It involves natural law, not supernatural intervention. Physical process, not metaphysical mystery. The cosmos is not a creation. It's an eternal pattern of change, sometimes expanding, sometimes contracting, sometimes inflating, sometimes bouncing, always transforming, always existing, never truly starting or ending in any absolute sense. We're part of this transformation, temporary arrangements of atoms assembled by the cooling aftermath of one particular bang in one particular region of an infinite multiverse, or one particular cycle of an eternal recurrence. We exist for a brief moment, aware and curious, attempting to understand the larger pattern we're embedded in. And what we've learned is humbling. We're temporary witnesses to an eternal cosmic dance. The universe is far older, far vaster, and far stranger than we imagined. Our bang wasn't the start of everything. It was barely even a start, just one more transition in a reality having no beginning and needing none. Nothing never existed. The void was never empty. Reality is eternal transformation, and we're fortunate enough to witness one brief phase of it. That's what existed before our bang. That's what exists now. That's what will exist forever. Not nothing, everything. Gaze upward into the darkness and locate that dim cloudy stripe of stars stretching overhead. What you're observing is our galactic residence, a massive rotating star system housing 400 billion suns. Yet something may surprise you. Even with all our aspirations for cosmic exploration and every tale of traveling between galaxies, we'll most likely never depart from this galaxy. Not in 1,000 years, not in 1,000,000 years, and probably never at all. The cosmos has erected barriers around us. These aren't barriers made of rocks or metal, but barriers created by enormous distances, vast time periods, and the basic rules of how reality works. If you love the content, consider leaving a like and subscribing to the channel. Get ready, we begin. To grasp why we cannot leave the Milky Way, we must first comprehend the staggering distances separating us from other galaxies. Andromeda, our closest large galactic companion, sits 2.5 million light-years distant. This figure is so enormous it becomes meaningless without context. Light travels faster than anything else in existence. Yet it requires 2.5 million years to journey from Andromeda to our location. The starlight you observe from Andromeda this evening departed that galaxy while our early human ancestors were still learning to craft stone implements. However, distance represents only our initial obstacle. The cosmos isn't standing still. It's getting bigger, and this expansion keeps accelerating. Currently, Andromeda actually approaches us and will crash into the Milky Way roughly 4.5 billion years from now. Meanwhile, every other significant galaxy races away from our position. The greater their distance, the faster they retreat. Most galaxies already move away quicker than we could ever hope to pursue them. Recent observations from the Hubble Space Telescope and James Webb Space Telescope have revealed galaxies located over 13 billion light-years away. Due to cosmic expansion, those same galaxies now sit over 30 billion light-years from us, moving away at velocities exceeding light itself. Space itself can expand faster than light, carrying galaxies along with it. The Sloan Digital Sky Survey, among the most extensive astronomical mapping projects ever attempted, has charted millions of galaxies and verified this cosmic expansion. Every galaxy outside our local group, the small cluster of galaxies gravitationally attached to the Milky Way, will eventually vanish beyond our cosmic boundary in approximately 100 billion years. Any future civilization in the Milky Way will peer outward and see nothing but emptiness beyond our local cluster. Suppose we remain hopeful. Imagine we could construct a vessel traveling at 99% of light's velocity, far beyond what current physics indicates as feasible. Even at this astounding velocity, a trip to Andromeda would consume over 2.5 million years from Earth's viewpoint. Because of time dilation, the travelers would undergo a briefer journey, perhaps 40,000 years. Yet that still exceeds the entire span of documented human civilization. Andromeda is the simplest target since it's the nearest major galaxy, and it moves toward us. Every other galaxy presents an even more unattainable challenge. The Triangulum Galaxy, third largest in our local group, lies 3 million light-years distant. The closest large galaxy cluster, called the Virgo cluster, sits over 50 million light-years away. At 99% light velocity, that represents a 50 million year voyage from Earth's reference frame. The energy demands for such voyages are overwhelming. According to Einstein's special relativity, verified by countless particle accelerator tests at CERN and Fermilab, pushing mass to near-light velocity requires exponentially growing energy amounts. To propel a single kilogram to 99% light velocity demands energy matching the total power production of the United States for multiple years. For a realistic spacecraft weighing thousands of tons, you'd require energy equivalent to transforming entire planets into pure energy. Recent investigations by NASA's Breakthrough Propulsion physics program, and continuing research at places like the Tau Zero Foundation have examined every conceivable propulsion method, from fusion engines to antimatter drives, from light sails to theoretical faster-than-light systems. Every examination reaches the same sobering result. Even reaching nearby stars within our galaxy pushes the absolute boundaries of physical possibility. Intergalactic travel is exponentially more challenging. The Voyager missions provide a reality check. Launched in 1977, Voyager 1 now sits over 23 billion kilometers from Earth, making it humanity's most distant object. At its present velocity of 17 kilometers per second, reaching the nearest star, Proxima Centauri, would require over 70,000 years. Reaching Andromeda at Voyager's pace would consume over 40 billion years, 3 times the universe's current age. Velocity isn't our only barrier. Intergalactic space isn't merely empty, it's the most vacant environment in the cosmos. The region between galaxies holds less than 1 atom per cubic meter. That's a trillion times less concentrated than the air filling your lungs. This cosmic emptiness stretches for millions of light years in all directions. It's an ocean of nothingness, making the space between stars appear crowded by comparison. Recent observations by the Cosmic Web Imager and studies of intergalactic material have shown this space isn't completely vacant. Traces of hot gas and dark matter exist, but these traces are so thin they practically don't exist for any useful purpose. A spacecraft entering intergalactic space would become more isolated than anything imaginable, unable to refuel, repair, or resupply for millions of years. The mental and physical challenges are equally overwhelming. Humans developed on Earth, suited to its particular conditions. We require continuous supplies of food, water, and breathable air. We need shelter from radiation, consistent temperatures, and gravity for our bodies to function properly. Building a self-sufficient environment that could endure millions of years exceeds our present capabilities and possibly exceeds what's physically achievable. Consider what we've discovered from space stations like Mir, the International Space Station, and China's Tiangong. Despite our finest efforts, these sealed systems need constant resupply from Earth. They experience equipment breakdowns, air leaks, and deterioration over mere decades. Expanding this to a million-year journey creates problems we don't even know how to begin addressing. The basic rules of physics themselves work together to keep us confined within our galaxy. It's not simply that intergalactic travel is hard, the universe appears specifically constructed to prevent it. Every breakthrough in physics over the last century, from Einstein's relativity to quantum mechanics, has only strengthened these cosmic barriers. Special relativity, verified by thousands of tests since 1905, establishes the ultimate velocity limit. Nothing possessing mass can achieve light speed. The Large Hadron Collider regularly accelerates protons to 99.9999% of light velocity, requiring the energy consumption of a small city. Yet those final decimal places toward true light velocity would demand infinite energy, not just in practical amounts, but literally infinite. The mathematics is ruthless. As velocity nears light speed, mass effectively grows toward infinity. This isn't merely theoretical speculation. We witness it daily in particle accelerators worldwide. The Stanford Linear Accelerator, Fermilab's Tevatron, and CERN's Large Hadron Collider all confirm that no amount of energy can push massive particles to light velocity. If we cannot accelerate a single proton to light speed with our most powerful machines ever constructed, how can we hope to accelerate a spacecraft? Modern physics offers potential shortcuts. The Alcubierre drive, suggested in 1994, proposes warping space-time to travel faster than light without locally violating the speed limit. NASA's EagleWorks laboratory has even conducted small-scale tests. However, every analysis uncovers the same problem. Such a drive would need exotic matter with negative energy density, something that may not exist in the required quantities anywhere in the universe. Dr. Harold White at NASA refined Alcubierre's mathematics, showing that energy requirements might decrease from Jupiter's mass energy to merely that of Voyager. But merely is relative. We're still discussing converting 700 kilograms of matter entirely to energy and somehow directing it into warping space-time. That's just for a small spacecraft, not the generation ships we'd need for intergalactic colonization. Wormholes present another theoretical option. Solutions to Einstein's field equations, developed by physicists like Kip Thorne and Michael Morris, demonstrate that shortcuts through space-time are mathematically feasible. Again, they need exotic matter to remain open. Every attempt to locate or create such matter has failed. The Casimir effect shows tiny negative energy densities between closely positioned plates. However, scaling this up to a traversable wormhole may be fundamentally impossible. Recent work in quantum gravity, including string theory and loop quantum gravity, has only reinforced these restrictions. Dark energy adds another layer of impossibility. Discovered through observations of Type Ia supernovae by the Supernova Cosmology Project and High Z Supernova Search Team, dark energy accelerates the universe's expansion. Every moment, galaxies grow farther apart, and the energy needed to travel between them increases. We're not racing against a static obstacle, but an ever-growing one. The integrated Sachs-Wolf effect, observed by comparing the cosmic microwave background to galaxy surveys, confirms that space itself stretches between galaxies. The BOSS survey and Dark Energy Survey have mapped this expansion in detail. Galaxies more than approximately 16 billion light-years away already recede faster than light. Not moving through space faster than light, but carried by expanding space itself. We could never reach them regardless of our technology. Time dilation offers false hope that becomes deeper despair. At 99.99% light velocity, time dilation would make a journey to Andromeda feel like only 3,500 years to travelers. Yet that's still 35 centuries of human generations living and dying in a metal container. More distant galaxies would require proportionally longer subjective times. The twin paradox isn't just a thought experiment. It's been confirmed by flying atomic clocks on aircraft and observing muons created by cosmic rays. GPS satellites must account for both special and general relativistic time dilation to maintain accuracy. Every confirmation of time dilation is another confirmation that while travelers might age less, the universe outside continues its relentless expansion. Radiation presents another fundamental barrier. Intergalactic space is flooded with cosmic rays, high-energy particles accelerated by supernovae, active galactic nuclei, and other cosmic catastrophes. The Oh My God particle detected in 1991 carried energy equivalent to a baseball thrown at 60 miles per hour, all in a single proton. Such particles would penetrate any conceivable shielding. At relativistic speeds, even ordinary hydrogen atoms become lethal radiation. The interstellar medium, sparse as it is, would strike a near-light-speed spacecraft like a constant beam of particle radiation. The faster you travel, the more deadly space becomes. Calculations show that at 99.9% light speed, the radiation dose would kill any biological crew in minutes, regardless of shielding. Thermodynamics imposes its own restrictions. The second law states that entropy always increases in isolated systems. A spacecraft traveling for millions of years would face inevitable deterioration. No machine operates forever. No closed ecosystem maintains perfect recycling. Every system tends toward disorder, and the timescales of intergalactic travel guarantee that entropy prevails. Recent studies of closed ecological systems, from Biosphere 2 to various space station experiments, show how rapidly isolated systems degrade. Unexpected chemical reactions, material fatigue, and biological evolution all contribute to system failure. Every long-duration space mission we've ever conducted has taught us the same humbling lesson. Space tries to kill us in ways we're still discovering. Valery Polyakov spent 437 consecutive days aboard the Mir space station. Scott Kelly spent 340 days on the International Space Station while his twin brother Mark stayed on Earth, providing NASA with invaluable data on long-term space exposure. The results were sobering: bone loss, muscle atrophy, vision problems, genetic changes, and psychological challenges we're only beginning to understand. The twin study published in Science in 2019 revealed that Scott Kelly experienced changes in gene expression, cognitive decline, and DNA damage during his year in space. His